Okay, good morning, everyone. Can people hear me?
Yeah.
Wonderful. Great. Good morning. So presumably everybody is following along with the lectures and is doing reasonably well with the homeworks. I think we should have homework 1 back to you reasonably quickly. I mean, I think our goal in general is about 8 days from the time it was due. You know, everything's a little bit subject to you know, moderate complications due to technical difficulties, but that's the intent. Let's see. Does anybody have any questions or logistical comments, either from the staff or from students? Kevin, I'm not forgetting anything?
No, I mean, other than we hope to post homework 2 within the next few days.
Yeah.
But other than that, I think we're ready to go.
Okay, wonderful. Okay, awesome. So last time we were talking about our first example of a model for classification, right? And classification, if we recall, is this idea that we might want to take a bunch of examples which are represented as features and make predictions that are not necessarily real valued, but instead belong to some discrete set of classes. And we were focusing on the binary case, right? So we were either labeling things as -1 or 1, which is equivalent to labeling things as 0 or 1, but it's particularly notationally convenient for us. And we were specifically thinking about logistic regression, right? So logistic regression is a linear a way to classify our data, which is making the same assumption that we were making previously, in the sense that we want to be making a decision as a linear function of our inputs, whether we're going to label individual instances as positive or negative, but it uses a particular class of functions to do that, right? So the class, specifically what we were thinking about last time, there's a bit of a lag. Hopefully that'll go away shortly. And let me know if that continues to be an issue. Okay, so specifically, the assumption that we make is that the probability of either a positive or negative label takes the following form, right? And this is just a particular assumption we can make. And if we make this assumption, right, then we have a particularly nice sequence of things that we can say about the minimizer of this assumption, right? Or sorry, the minimizer here that we can define. And okay, so if we were looking at the probability that y equals 0 given a model w and x, that's just equal to this simple form here, right? And this has just been written out explicitly emphasizing that we may want to think about the intercept of the sigmoid differently than the other coefficients, right? And there's a nice reason. There are a nice sequence of reasons for doing so. The primary one is that this W0 really does act as something that governs the intercept, just like in a standard linear, just like for a standard linear function. We often have sort of special things to do for that intercept, just as was in the case when we were thinking about these squares, right? A lot of you on homeworks have been asking questions about sort of, am I supposed to regularize this thing? Am I supposed to standardize this extra column of ones? There's always a little bit of extra work that goes into like some special treatment that sometimes has to happen for this particular, for the parameter that governs the intercept. Okay, so someone asked a nice question, and I didn't do a great job answering it last time, about precisely what we meant by this being a linear decision, a class of linear decision functions. So if we look at the ratio between the probability y equals 1 given w and x divided by the probability y equals 0 given w and x, right? We can just write that out in a functional form. But let's think about what this means intuitively, or what this means if we actually like interpret it. What this is saying is the probability y equals 1 given w and x over probability y equals 0 given w and x. When that's greater than or equal to 1, that means that y equals 1 is more likely, given the features we see, than y equals 0, right? So y equals 1 is, and apologies, y equals 1 is more likely, right? And when this is less than 1, that implies y equals -1 is more likely. Okay, so that decision rule is going to be the one we want to think about, right? And in this format, it doesn't look like a linear decision rule, right? We have some linear function, but we're taking an exponential. However, when we actually take log of this thing, right? Then asking when this is greater than or equal to 0, and using that as a decision rule gives us the linear decision boundary that we were talking about last time. So again, if this is our vector w, then this just induces a linear decision threshold for saying on one side, we're going to be labeling things as positive, and on the other side, we're labeling things as negative, okay? Hopefully that clarifies a not so great answer I gave last time. So as we were talking about last time, we generally need to decide on a model, right? Make assumptions, right? And in this case, we did some of that already. We've chosen a loss function, right? And then the question becomes how to pick the function which minimizes loss on our data, right? And for the case of least squares and for ridge, we found closed form solutions, right? There was an explicit way to write down the function which minimizes our loss function on our data. That wasn't the case. That wasn't the case when we were thinking about lasso. And it also won't be the case when we're talking about logistic regression, which means we're going to actually have to like work a bit harder to find the function which minimizes logistic loss on our data. Okay, great. So let's just remind ourselves what exactly we were talking about, right? We were talking with slightly more formal notation. We were thinking about the setting where we have n IID data points, where we make this assumption, right, that the probability of our label follows the sigmoid form. And that means that when we write down the maximum likelihood estimator for our set of parameters, we get the following particular form, right? And this particular form actually looks a lot like, if you sort of blur your eyes as opposed to squinting your eyes, many, if not most, of the MLEs you'll see in this class and just more generally, and many other machine learning problems will end up looking a lot like this, right? They're asking you to find the minimizer of a sum of things where each individual term represents one of the samples you see, and the inside of that sum, right, each term, which is representing one sample, just looks like this, right? Has some simple form. And if we think about logistic loss, right, the LI is just written nicely like this. Squared loss also has this format, and many, many other loss functions also have this format. Okay? So this is a way to think about the maximum likelihood estimator and many other optimization problems, which sort of can help think about how you might actually find that minimizer. Okay, so if you want to actually find the maximum likelihood estimator for logistic regression, the question becomes how to do this minimization problem, right? And we sort of waved our hands last time and said, okay, well, we don't know how to find, last time before? Last time, anyway. Thanks. So we didn't know exactly how to find a closed form. There is no closed form for lasso, and we said, well, that's okay. The loss function is convex, so you can throw a solver at it. And we're going to spend more time today talking about precisely what we meant by saying the loss function was convex, how we knew it was convex, playing around with a couple of properties of convexity, and showing how you can actually solve things when they are convex. Okay. So in this setting, right, if we're thinking about logistic regression, it's also going to be the case that this is a nice convex function, right? That this function, which we're referring to as j of w, that this is convex. So that's great because convexity buys us a bunch of things, right? One of the sort of fundamental properties of a convex function is that there is a unique optimum, like there is a global optimum, right? It's unique, and there won't be other local optima that we get stuck in, right? So there will presumably be some problems on homework 2. We haven't totally finalized that yet, but there will be some problems on homework 2 for you to think about why that's the case. And as I mentioned before, in this case and in the case of lasso, there's not a closed form solution to, I think in this case should be minimize this function that we care about. But we're going to be able to optimize for finding a minimum of j of w. Okay, so I'll come back to that in a minute, but I want to first take one more or a couple more minutes to talk about logistic regression. And one of the problems that we've seen for linear models when we were talking about regression as opposed to classification, which is the problem of overfitting. And I want to ask whether anyone sees when finding the minimizer of this j of w might overfit our data. And I'm going to wait a minute and see if anybody has some idea as to when this might overfit. Feel free to unmute yourself if you have something to say about that.
Is it maybe when like you only have examples from one class? Maybe, I don't know.
Sure, that would be one case where we might overfit, and that's a special case of the particular phenomenon I was talking about, right? Or I was sort of hoping, I will talk about, which is the following. So suppose our data is linearly separable, which means that there exists a linear function which perfectly separates our data, right? In this case, right, this linear function perfectly separates our data. And what does it mean if we picked a W which classifies our data perfectly? That means that, what does it mean about X transpose I dot W? It should always have the same sign as YI. Okay, so when that's true, right, we have that this part, right, is always greater than or equal to 0, right, because we're multiplying things together that have the same sign, which means we're looking at log of 1 plus negative positive number, right? And that's going to imply that we'll ultimately be able. Okay, that's going to say that, like, we're going to be able to do something funny with this loss function that maybe wouldn't happen in other cases. And roughly what happens is that, like, if you think about the precise form of this loss function, right, as you drive the weights up, it's going to make this this function grow smaller and smaller and smaller, right? Closer and closer and closer to 0. So that's, and if we just go back here and look at this precise function, okay, what we're saying here is, like, we're going to be able to, if you think of X as some function of W, right? As we pick larger and larger W, we're going to be able to drive our loss function lower, even though we're sort of making the same classification decisions, right? So we'll be able to make, we'll be able to perfectly label all of our data, and despite that, continue to be able to decrease our loss function by increasing our weights. And that's problematic for a bunch of different reasons. But one of the primary ones is there are many, many different functions that we can think of which might perfectly separate our data. And the larger and larger W are going to ultimately tend to overfit, right? And you can think a little bit more, and we'll probably have you play a little bit more precisely why larger weights overfit. But the intuition is that the sigmoid gets steeper and steeper as we use larger and larger weights, which give the same classification decisions on our data set. So one idea to reduce this problem or to mitigate this problem is, just like in the case of regression, you can think about penalizing the high weights to prevent this type of overfitting, right? And we've talked about.
Jamie.
Yes.
Jamie, do you mind if I just jump in here for a second? So overfitting, as Jamie's been mentioning, like, it's a problem with, like, a statistical issue, overfitting, and, you know, bad things happening with that. But, like, there's also just a very practical issue with the weights going off to infinity. Jamie's about to talk about an algorithm that is going to optimize this function, and if you keep sort of waiting for this function to drop, and your weights are going off to infinity, just numerically, you never want things to go off to infinity. That's a very bad thing to ever happen on a computer.
Yes.
And so, like, just from a very practical standpoint, having the weights going on to infinity is just a big, big problem computationally.
That's right.
Regardless of statistical issues, which are a real thing, but.
Right, and that's also, you know, one of the things that can be a nice property of a loss function is for a loss function to be bounded from below. and right. So weights going off to infinity is a particularly bad thing. And basically what that means, even though the loss function is bounded from below, it sort of like, yeah, the weight going off to infinity while you drive the loss to zero is a problematic thing numerically. That's right. Thanks, Kevin. Okay, so if we were going to add a penalty to our loss function to avoid high weights or overfitting, right? That would look something like this if we were going to use like an L2 regularizer, for example, which is a reasonable thing to do, right? And for your particular problem, you may or may not need to do this, depending upon, you'll probably need to do some kind of regularization. L2 regularization is one type. We've also talked about L1 regularization, and there may be other types that are particularly appropriate for the setting you're thinking about. And I'm just writing this on a slide here so that you can go back and refer to it, right? This is one way you can regularize conditional log likelihood. And I want to just call out that here we're not regularizing the W naught, right? This was what was called W naught on other slides, right? And was called B when we were talking about least squares. Apologies for that. But this is the offset parameter, right? This is not governing slope, right? In any direction. It's just governing the point at which our function hits the intercept if we're talking about 2 dimensions. And it's a particular, there's no reason to regularize that per se, right? We're not actually getting benefit by driving it to a really large value. And it's, that's something that sort of doesn't tend to overfit, and you can sort of sit down and do some of the math to think about why precisely that is. Okay, so now we're going to talk about sort of the primary workhorse of like maybe most of computation being done in the world right now. Certainly the primary workhorse computationally for most of machine learning and machine learning technology, right? Which is gradient descent. So I'm going to talk about a particular algorithm which is generally used to optimize convex functions, right? We've sort of been saying, oh, there's like solvers, they can do this stuff, but we think it's important that you actually understand from a conceptual and also mathematical level what these particular solvers are doing, and also understand convexity at a sort of more fundamental level than just like we sort of know what the shape looks like. Okay. Before I do that, does anybody have any questions about logistic regression before we move on?
Yes, I have a question about the definition of JW in the previous slides. So I'm wondering that is JW the definition of loss function or the expression for W of maximum likelihood estimator?
So this slide, okay, so so JW here is our loss function, and it's also our maximum likelihood estimator minimizes it.
Yeah, got it. Thank you.
It's just hard for me to kind of reconcile the idea of overfitting in terms of here, because it's like you're trying to fit some kind of like a decision boundary. If your data is perfectly linearly separable, and like, you can find that perfect hyperplane in here, like it's just somehow like, reconciling that idea with like the way we talk about overfitting in terms of like, regression or something, or yeah, or fitting like, like fitting too high degree of polynomial data, like it, to me, it just feels so weird to me that we call that overfitting here.
So
That's a
I-
good comment.
Yeah.
I agree. When you're just looking, so the problem here is that we're looking at like 20 points in 2 dimensions. Okay, so like things look really like kind of ridiculous. Like, no, this looks like it's
Yeah.
fitting it totally perfectly well. But if I had 20 points in 20 dimensions, which we can't visualize, you might be thinking a very different story. And so
Yeah.
that's kind of what you should be thinking about, not 20 points in 2 dimensions, but like 2 points in 2 dimensions. And then thinking about this W going out to infinity. Now that argument is a little absurd, but like to visualize this a little, to try to get some understanding of like why this might be a bad idea from an overfitting standpoint, think about the polynomials. Think about like fitting a 12-degree polynomial to 2-dimensional data, and it basically winding they have this super curvy decision boundary going through these points. And then you might say like, okay, yeah, I'm probably overfitting here. I'm getting 0 training error, but like it's so wiggly decision boundary that like there's no way that this is true. But it's a great question. Like, but by looking at linear functions in low dimensions, it's very hard to imagine anything going wrong. But the reality is
linear functions in high dimensions with a relatively small amount of data behave a lot like high degree polynomials with small amount of data. In this particular sense, right? That they like, it's not like actually squiggly, but it's sort of getting perfect error while like sort of sacrificing the simplicity.
Right.
Yeah, maybe like Jamie and I have mentioned like multiple times in this class that like it's hard to picture anything higher than 2 or 3 dimensions. And so like we have to use these sort of imperfect examples of visualizing high degree polynomials in low dimensions to gain intuition about this kind of stuff. Also like the spikiness of the L1 ball. Some of this stuff is just sort of like, you see it enough times and you just sort of start believing it, I think. Maybe it may not actually get understanding, but you actually just start believing it. And then you become a little bit more comfortable with it. But it's difficult to picture this stuff in high dimensions.
Gotcha.
I totally agree with that. Yeah. Yeah. So that's a good point. And believe it or not, linear functions can overfit your data, right? So like maybe, this is not like answering your question exactly, but if you have a linear function in some number of dimensions and your data set is like fewer than that number of dimensions, it's definitely going to be possible for you to overfit your data set. And I think it'd probably be good for us to think about some examples for everyone to work through on a homework to think about that. So I agree that thinking about large W maybe doesn't do that intuition, but like linear functions still can overfit data in high dimensions, relative where the dimension is high relative to the size of your data set. Okay, so good. Any other questions before we move forward?
I have a quick question. Oh, here, go ahead.
I was just gonna say, it looks like there's some questions in the chat that we haven't addressed yet.
Okay, so why don't, would you be willing, was that Swati, would you be willing to call on people? I'm trying to pull up the chat, hold on one second. Okay. Okay, so it's Josh, are you there? Would you be willing to tell me which of these haven't been addressed?
I think just the most recent one.
Okay, just the most recent one. Linear functions type. Okay, so so
maybe I'm responsible for that one.
or I am. I don't know. Go ahead, Kevin.
So what I mean by that is when we went through this polynomial, when we did our basis expansion, when Jamie talked about how to basically change your data from this low dimensional, like one-dimensional object to all polynomials of it, that is effectively projecting your data up. Basically, you're changing just x into x squared, x cubed, x to the fourth, x to the fifth. And so you're basically blowing this thing up, but we can visualize it now because the x variable, like we can actually visualize what that looks like in one dimension with a curve, and that gets very, very wiggly. But basically, it's equivalent to actually going up to the, in a 7-degree polynomial, projecting your data up to 7 dimensions, and then fitting a linear hyperplane there. So like you are actually fitting something in 7 dimensions, but like by because you did the explicit basis transformation, you can visualize that polynomial in 1 dimension, and you can see how wild it is, and you can see how easy it would be to overfit in these lower dimensions if you just like fit through every single data point. You wouldn't really trust that curve, and the same phenomenon is happening in higher dimensions. It might be.
Sorry, go ahead.
Yeah, it might be better to take this one offline into office hours.
Yeah.
Because drawing pictures could help here.
Great. It sounded like there was another question. Feel free to unmute yourself and ask questions.
Yeah, I had a quick clarification question about this J of W, this loss function that we're attempting to maximize or minimize. So it's a identifier variable, right? You're either in the right classification or the wrong. It's either y equals 1 and the training data is y equals 1, or y equals -1, right?
So I'm not sure precisely what that has to do with. Sorry.
So basically, how are you measuring how far off your model is, right? If you're classifying in different groups, y equals 1 or y equals -1, you're kind of on a binary system as well, right? You're not getting real values on how far off your model is, right?
So if we think of this particular loss function, x transpose w is a real number, right? And yes, we are using x transpose w in a sort of, we are interpreting it and making sort of a classification decision to decide either +1 or -1, but xi transpose w is a real number, and we're using that real number when evaluating the loss of our particular w.
Okay, yeah, okay, thank you.
Looks like Kevin has something to say about that too. No?
No.
Okay, I saw you briefly unmute.
Well, I was just gonna say that yes, the sign of xi transpose w is our predictor, but you really get a real valued loss with x. You get a real valued number xi transpose w, and as you recall from homework 0, if you're curious about a sense of margin or how far away is a point xi from this decision boundary defined by w, that is exactly a problem that you did on homework 0 actually, which is basically that distance to the hyperplane.
Yep. And we'll have some other senses of margin coming up when we're talking about SVMs, for example. Yeah, Leah.
Oh, hi. Yes, my name is Leah. I had a question about, I had the same question about like, do you eventually develop an intuition for overfitting? And I was just, so I guess now I'm wondering, because you already said that you sort of do, I'm wondering if you have any tips on kind of how to develop that intuition. I suppose one answer might be just do it a bunch and see what happens. But that is what I'm wondering, if you have any tips for developing intuition for when something is overfit.
Yeah, so in general, like a poor man's rule of thumb is that, so there are several, one of which is if you count the number of parameters of your model, right, And in this case, right, if we're thinking about a d-dimensional linear function, that's p plus 1 when we include the intercept, it's certainly the case that like you usually want the number of parameters to be relatively small compared to the amount of data you have, right? That's like one thing you can look at. That's obviously not capturing the thing we're talking about right here. There are actually many ways you can overfit your data. Another intuition is that you generally will want the representation of the function you're learning to be compact in some sense, right? So like if your W's are going off to infinity, that's implying, you know, that you couldn't describe your W in some like nice numerical way on your computer, right? And similarly, if you have a really, you know, high degree linear function, you need a lot of space on your computer to actually represent that, right? In both of those cases, you might need to use a lot of memory to represent the classifier or the model you have learned. And both of those, there is a way to argue that if like you can basically represent your model in a compact way, right, using relatively little data, or sorry, using relatively little space on your computer, there are actually formal ways to argue that that will guarantee some reduction in overfitting. There are many different ways to do that, and we're not going to talk about that second way at all in this class, but that's one of my favorite pieces of statistical learning theory, right? Like there are various tools to argue that you won't overfit too much. And we'll talk a little bit about some of them, but not all of them.
Yeah, and I just like to echo that, you know, if you're looking for, I just want to echo exactly what Jamie said about if you're looking for just intuition and a poor man's sort of metric of just like parameter counting, like how complex is the model, and you should be thinking of that doodle that we showed many times during the bias and variance trade-off discussion of like when the number of parameters is small, or like when the complexity of your model is small, the bias is high, and as I increase the complexity, the bias decreases. But because I have so many parameters to fit, the variance increases. So with very few parameters, the low complexity, there's very few parameters, very little variance in estimating those. But if I'm trying to estimate, you know, 1,000 numbers instead of just one, I'm going to have a lot more variance in those estimates. And so that is the sort of plot you want to think about in terms of complexity and bias and variance and intuition towards overfitting. As you go to the higher sort of on that right-hand side of that plot, as that variance goes up and the bias is going down, you're getting in the territory of overfitting.
Yeah. And the reason we say that that's a poor man's estimate is that like, you know, just to say one quick other thing, apologies. For those of you who are training neural networks, right? In many cases, the number of free parameters that people are using, like research or industry grade models, is much higher than the number of data points that they have, right? And it's really confusing and perplexing, but somehow, despite the fact that the number of free model parameters seems to be substantially larger than the number of data points that they have, we seem to not be seeing as much overfitting as we might expect from this poor man's approximation, right? And the other direction happened too, right? That like a model can be complex even if the number of model parameters is relatively low. Okay.
Thank you.
You're welcome. Okay, are there any other questions before we go on? Okay, great. So we were just about to talk about how we actually want to do this optimization, right? We actually have this J of W, and we want to understand how we can minimize it. And by how we can do that, I mean actually designing some kind of algorithm which will do so. Okay. So, I've belabored this a bit. What did we mean by the fact that our loss functions are convex and that we can sort of throw those to some optimization? Okay. So, notice that, I did a bit of setup before, sort of suggesting that what we're going to be doing is finding the minimizer, right, of something that looks like this, right? Some function that's a sum of some little losses, right? And the sum of convex functions is also convex, right? So if each of our individual terms that we're measuring on each of our data points is convex, then the sum of them together jointly is also going to be convex, which is great because the loss functions we've been thinking about on each data point are convex. Therefore, summing them all together, we also have a convex function. Okay, so I think we haven't actually formally defined convexity in the lecture yet. So, but it looks like they're okay. So we haven't defined convexity yet actually in lecture. So let's talk about precisely what we mean when we say convexity. Okay. So we have some function, right? In this case, you can think about this black line. Right? And the black line is defined. We're doing everything briefly for a moment. Think about this in sort of a single dimension or two dimensions, right? Where we have a single input and output dimension. And what convexity generally is defined to mean is one of the following two definitions. The first one is saying if you look at the function f, right, this function f right here, and you look at if you look at basically the line segment between the value of f at x and y, which is just this, right, this here, and you move lambda between 0 and 1, right, which basically means you're moving, when lambda is 1, you're looking at this point. And when you're looking at lambda equals 0, you're looking at this point, right? If you look at any point on that line where you're moving between x and y, you see that this line segment defined by the average value between f of x and f of y is above the point you would get evaluating f at that same point, okay? This point right here, okay? That's this term right here. So what this is saying is if you look at 2 points, 2 inputs to your function, right? And you draw a line between them, right? That line will always lie above the function, right? And that's a very useful property. And it's equivalent to this other one, which I'll tell you about now, which involves gradients as opposed to just some like nice representation of like averaging the function value in some sense between 2 points. Okay, so if you look at the value of the function at some point x, right, and then you try to understand what that will mean for the value of the function at f of y, one thing you can do is you can take the gradient of the function at x, right? And then multiply that by the difference between y minus x, which is just looking at this. This is the gradient right here, right? And what this is saying is f of y minus f of x is at least the gradient of f at x times y minus x. Okay, so these are two equivalent definitions of convexity of f. And I'm going to briefly mention, we won't really use this too much in lecture, although this is like a very practical and useful thing to know generally, and it may come up in some homework in the future, is that when you're looking at a function that doesn't have derivatives defined everywhere, it's not everywhere differentiable, right? The gradient may not be defined everywhere, for example, here, right? Then what you'll usually want to think about is functions that operate as subgradients, right? So a gradient, you guys all know what the definition of a gradient is. A subgradient is just some function that we can place in this definition instead of the gradient, right? It's just saying if there's some function which at any particular point, right? G is a subgradient at x if when you look at f of x and you add G transpose and multiply that by the distance between y and x, right? Then that will be a lower bound on your function value at y. And that's useful to use when you don't actually have, you don't have a definition of a gradient of your function at some points. And that'll come up all the time in practice. So you'll, in the case that the gradient doesn't exist, you can place in its place some subgradient. Okay, so let's briefly talk about why these two definitions of convexity are equivalent. 1 second, sorry about this. Okay, so does anybody have some idea for why it might be the case that these are equivalent? You guys should remember some stuff from calculus, right? Okay, so if we look at this one, right? Okay, so we know that f of lambda x plus 1 minus lambda of y is at most lambda f of x plus 1 minus lambda f of y. Okay? And this is just equal to, oh, sorry, that's, okay, so now we have lambda f of x plus f of y minus lambda f of y. Okay. So that can be written as lambda times f of x minus f of y plus f of y. Okay, so okay, so if we then look at, sorry. Okay, so we can then look at f of x minus f of y. Sorry guys, I just lost my train of thought. Okay, so then, right, so we're trying to find a lower bound of f on f of y, right? And so far we have a term as a function of this god-awful thing and f of x minus f of y. So what we want to do is use something that, okay, so then this is equivalent, or this implies that f of y is greater than or equal to lambda times f of y minus f of x plus f of lambda x plus 1 minus lambda y. Okay. And then I think we want to think about what happens as lambda grows quite small, right? And as lambda grows small, right? Then this no, sorry. Kevin, can you help me out here? I seem to have screwed something up. Sorry.
Divide the right-hand side by the left-hand side.
Great, thank you. Wait, right-hand side by the left-hand side. You mean this guy?
On the previous slide.
Yeah, great, okay. Wonderful, thanks. Okay, so if we divide this by f of lambda of, wait, yeah, lambda x plus 1 minus lambda of y. Okay, then what we see is we have, sorry guys, I just like scoot this up. Sorry, go ahead.
I just said it's all good.
Okay. Yep. Sorry, I'm like staring at it. I'm too close to it, and I
Yeah.
Yeah, Kevin, go ahead, save me.
So no problem. Okay, so what you want to do is rewrite, say f of lambda x plus 1 minus lambda y as so you've got it right there. But now what you want to do is basically bring over. I'm sorry. Yeah. So yeah, you've got it right there. That's good. And now you want to subtract f of y on both sides. So you look at the top left expression, subtract f of y, and the bottom right expression, to f of y. And so now what you've got is f of lambda x plus 1 minus lambda y minus f of y on the left-hand side, and lambda f of x minus f of y on the right-hand side. Now when you divide by lambda and take lambda to 0, that is you'll see it's the definition of the gradient.
Of the gradient, yeah. Okay,
yeah, so the trick is to make y be separated and then write it as
yeah.
And then
okay.
you'll see that it is the gradient.
Okay, yeah. All right, I will write this out more clearly in a moment after a lecture. Apologies for that. I think I'm not going to write it.
Can we also show that using the Taylor series expansion?
Sorry, I couldn't hear what you said.
Can we also prove that using the Taylor series approximation around x?
So the issue with that is, I mean, like you can write the Taylor series expansion and you'll basically get like approximate equality, right? Because those remainder terms. But convexity is a much stronger statement. It's saying that there is a strict sort of inequality, or there is an inequality going one way, and you can't really say anything about the other way. So the Taylor series is really just an approximation, and the higher order terms could make it negative or positive. Convexity is really saying that you have this very nice sort of expression, like you can all those higher order terms are actually negative effectively, and so you can just upper bound them by 0, and then you're done. And so convexity is a much stronger condition than what the Taylor series would suggest.
So and you could yeah, that's the yes. Okay, great. So good. So as we were talking about before, right? We have nice convex functions that we actually are trying to minimize, right? We're looking at the sum of a bunch of convex things, which is also going to be convex. And then the question becomes, how we actually minimize those, right? And we did just talk about like a couple of definitions of convexity, which are useful. And there's a natural, you might ask, like, why are we talking about this at all when we're talking about squared loss, right? Squared error, because we had a nice closed form expression for the loss when we were talking about least squares, right? Or sorry, a closed form expression for the model which minimizes that loss. But we didn't actually say that that was the way that you would actually want to solve for the W that minimizes this loss, right? And it's actually the case that most software won't do that, right? They won't sort of explicitly necessarily solve, like exactly do the matrix multiplication and inversion that we wrote out that explicitly defines the minimizer for W, right? It depends on whether or not you need a high degree of precision in your answer. It depends on various notions of sparsity, right? If lots of the points of if lots of the dimensions in your data set are 0, or similarly, if the least squares estimator is sparse, right? If you don't necessarily have a well-conditioned, right, like a sufficiently high dimensional data set relative to the number of data, full rankedness of your data set relative to the number of dimensions you're looking at, there are a whole bunch of different reasons why numerically and sort of algorithmically, your optimization software wouldn't actually just find the explicit minimizer and just do the sort of straightforward linear algebra that would be necessary to compute that, okay? Does anybody have any questions about that? Okay, we're just saying that, like, it's not the case that, like, the explicit form for the least squares estimator that we wrote down before is necessarily just like writing down in MATLAB. That explicit formulation is probably not the best way to actually compute the least squares estimator. Okay, so someone else was kind enough to remind us just now of the existence of a Taylor series approximation, right? So you have all taken high school calculus, so I would imagine you remember, or some equivalent course. The Taylor series approximation of a function simply looks at that function and asks, what can I say about that function's value at points near some x? And the way to answer that is that you can always write that in terms of the function's value at that point plus some, plus the derivative of the function at that point times the distance away you're moving, and then you can add many other higher order points as well, right? From higher derivatives, right? And as was mentioned before, right? You certainly can ignore, if you choose to ignore sort of the points beyond the first derivative, right? You might be tempted to use this as a way to argue equivalence between the two definitions of convexity we were working with. Unfortunately, right, all of these higher order terms that we're largely ignoring, and one that I'm not explicitly ignoring here, make that argument not go through, at least in terms of equality. Okay, so the Taylor series approximation suggests something kind of nice, right? So if we're thinking about a convex function, we may be at some point x, okay? And if we're trying to decrease the value of that function, one way we can do that is by taking steps in the direction of, we might want to take steps in such a way as to decrease the value of the function of f. And one way we can do that is by looking at the derivative. So this might be f prime of x. And so the gradient, the way we might do that is by taking steps in the direction, or subtracting off some amount as a function of the gradient at a particular step. So we might define, so f of x new equal to f of x old minus eta times the gradient of f of x. Okay, so it's something pretty simple, right? What we might do to actually approximate, to do some minimization of some nice convex function. And this is all that gradient descent does, right? And in one dimension, it's like really nice. You can sort of draw really elegant pictures. In higher dimension, it's a bit more complex. In this case, we just write x new is equal to x old minus eta of the gradient of f at x old. And the cartoons here are much harder to describe, right? Because if we're thinking about high dimensions, we just do a very poor job sort of conceptually. It's hard to describe them, and it's also hard for us to visualize them or sort of even think about them in any meaningful way. But the way you should sort of think about this picture is the following, right? We have now some convex function, right? And what we're doing is that we're taking steps towards, sorry, I see a question. What does the Taylor approximation have to do with this? The Taylor approximation sort of suggests to us something about the direction in which we might want to take steps to minimize the function. And that, yeah, okay, good, great.
Another way of it, yeah, there's tons of different ways to think about gradient descent. And like one possible interpretation that I like to think about is when we take this Taylor series expansion, we're saying that like f of x plus v is equal to f of x, this whole expansion here. And basically it's like you can write down your function, and like that Taylor series, if you go on forever, is true. Like that is your true function. But what we know about Taylor series expansion is that like if v is small, if this tiny step away is really a very small step, then actually all those higher order terms are pretty negligible, and they're like there's zero effectively. And so then you really just have f of x plus the gradient of f transpose v. And so what you're effectively doing is you're fitting a hyperplane to the function f at x. And then you're saying like the approximation is basically saying, look, my function is linear. It looks very linear, at least locally, in a small neighborhood around my point x. My function is very well approximated by just a linear function. And what that linear function is exactly the gradient of f at x. And so if you ask the question, well, I want to minimize this function f, I know locally it looks like a linear function where that linear function is defined by the gradient, then it makes sense to take a step in the negative direction of the gradient, because that is going to be the direction that minimizes that function, at least locally, the best. It's sort of the optimal thing to do in a very small neighborhood around x.
Yep. Thanks, Kevin. Yeah, I think that's a right. And also, right, when we're talking about convexity, one of the things we said was that sort of the gradient at some point x is a lower bound. So thinking about that as an approximation should like sort of only lead you towards smarter things, at least in the local sense. All right, so I'll give you a bit more of a pictographic description in a minute, but this is sort of the thing you should keep in mind, right? What we're doing in all of these cases is we're taking an old point and we're updating it to some new input, right? Some new point, some new W in this case, by decreasing, by subtracting off some amount, some eta times the gradient at that old point, okay? So I just want to define this. If you're thinking about doing this again and again and again, it's useful to actually define this in terms of some t that you're going to increase, okay? So maybe you start off with x naught equal to, I don't know, for example, you could start with 0, but this is some arbitrary point, right? And you start with t equals to 0, and then, you know, you can say while some stopping condition, and we'll talk about this in a second. What we want to do is just take a step, just take this exact step, right? Set x t plus 1 is equal to xt minus eta times the gradient of f at xt, and then set t equals to t plus 1. Okay, so what this is doing is it's saying, all right, we're going to, for some period of time, which I haven't yet decided what I'll use to actually stop this process, I will just continue to take steps in the opposite direction of the gradient at the point I'm currently at. Okay, okay. So let's go back to this drawing that we had before. Okay, and think about two things that I have sort of left underdefined at this point, right? The first of which is the stopping condition, and the second of which is sort of what is this eta parameter, right? And they're actually somewhat related, at least in the sense of the drawing I'm going to give you next. Okay, so if we start, say, let's suppose this is x naught, right? And let's say this is 0, for example, x equals 0. Okay, so what does eta tell us about what this algorithm is going to do? Anybody can unmute themselves and answer that question.
Like how much, like how much are you going to step in the direction of the, like how far are you going to go, right, in the direction of the gradient, basically?
Right. So if, for example, we have small eta, right? We might see ourselves taking fairly small steps, right? Okay, which would generally mean that we would want, you know, it would take more steps before we reach something pretty close to the minimizer, right? On the other hand, if our eta was large, right? I mean, depending upon how large, it would either just mean we'd get to this minimizer more quickly, or it might mean, right? It could mean just getting to the minimizer more quickly. Right? Larger, not gamma, eta. I think gamma is a fairly common, there are several Greek letters that are commonly used for to define gradient descent. Okay. If you started with even larger of an eta, you might see something somewhat crazy, which is that you might actually see that you're diverging away from the minimizer of your function, right? If you do something, if you have like a really big eta. Okay, so there's going to need to be some optimization of this eta. What's a good value? Okay, and a reasonable rule of thumb is if you see as you run this not yet perfectly well-defined algorithm, and you see that sort of the value of your loss function is getting larger and larger, your eta is too big, substantially too big. Your step size should be decreased. Okay? On the other hand, if you're seeing that things are converging really, really slowly, it might be the case that you want to think about choosing a larger eta, right? And so there's sort of a balancing act there, because if it's too large, you'll have problems in terms of even converging. And if it's too small, you'll have problems in terms of converging, but not in the same sense. It'll just take a long time to converge. Okay. So the last thing we still have to, and that's not giving you like some formal measurement of what your eta should be, and that's actually sort of, that's a problem more broadly with like using this both in theory and practice. There's no sort of tried and true statement about like what will always be the best thing, right? And there's sort of a no free lunch theorem that you could state here, right? That like if you just define a particular eta, even if it's optimal for your problem, there will be other problems for which it is not optimal. Okay, so finally, we have to decide what we want to put in this box right here. Actually, I want to not draw that box like that. Okay. We want to say, what is our stopping condition? At what point do we want to say that we are close enough? And the reason that we actually, you know, one thing we could say is like, well, we just watch until it converges or something. But what does it mean for this to converge? And we could say that basically, we want our gradient to be, we want either for it to be the case that our gradient at our point is small, and then we're willing to stop, right? While our gradient is large, we want to continue this. Or we could say we want to keep track of sort of how much our losses change from round to round, right? And there are pros and cons, again, to each of these choices, but let's start by talking about this one, the gradient of f of xt. Maybe if we say something about its norm being large, okay? So what this is saying is there's still a direction in which I can move to substantially decrease the value of the function, at least in like some local sense, right? It might not actually substantially decrease the value that much because we might just not have very far to go, right? Because this eta, you know, we might be pretty close in the in L2 sense to the minimizer. So like we might not actually be able to reduce the function value very much, but like there's still fairly steep curvature. Okay. Okay. There's a problem with using this, right? One of which has to do with sort of if we think about, we could end up in a situation where the function we were looking at has this shape, right? That could be somewhat problematic, right? If we have like f of x, this is x equals 0, f of x equals the absolute value of x, then you know, we might not want to do this, right? Because like if things are really nice and symmetric, you might end up bouncing back and forth. You might separately, as I mentioned, look at f of xt and f of xt minus 1, right? And if you might say, well, that's bigger than epsilon, right? Which is saying, I don't necessarily directly care about the gradient, right? I don't care if the gradient is large or not. I care if I'm continuing to make substantial progress in driving down my loss, right? And if I see that my last step, it still made some progress, I might still have some distance to go. So I might as well take another iteration with respect to this gradient. Okay. So if we talk about gradient descent with respect to least squares, right, we can actually explicitly write down the gradient of f, right? And we used this before when we were talking about sort of explicit, well, we didn't talk about the gradient. We took derivatives though. Maybe we did talk, yeah, we did take, we talked about the form of the gradient. And we can look at sort of what exactly the update rule looks like for least squares when we're using gradient descent. Okay? So this is something that we've seen before, right? This is just the format of the gradient when we're looking at the least squares loss. And then when we're thinking about what happens to our weight vector, right? Our weight vector is just equal to our old weight vector minus eta times this gradient at our old weight vector, right? Which, if you do a little bit of substitution in algebra, you can show is just equal to this term right here. Right? Don't know how I did that. Okay. Is just equal to this term right here. So that can also be sort of written out as, that can just be nicely written out if we think about this as in terms of like the optimal, right? This is the actual closed form that we were talking about before of our W, right? The W that actually minimizes our loss. So if we want to talk about sort of how far away we are from this minimizer, we could look at the difference between WT and W star. And let's imagine for a moment that like in round T, we actually got to W star, right? In that case, what we would see is that, sorry, I'm trying to understand what I wrote here. Okay, so I think, right, so if you wanted to understand sort of how far away we are from W star, okay, if we want to understand in round T+1 how far away we are from W star, we can just write that out nicely as a function of these terms we had before. And this should be equal to 0, right? So this gives us a nice way to measure as a function of how, of our previous round, right? If we say we are at WT, we can evaluate sort of how far we'll be away from W star if we take another step, just as a function of these parameters, right? And these aren't even parameters. These are sort of, yeah. Okay, so we're just about out of time, but I did have one or two other things I wanted to say. Okay, so the primary one was the following, okay? So if we want to think about sort of what least squares does in one step, we've defined that, right? We've said WT+1 is equal to WT minus a step in the direction opposite the gradient, or plus subtracting off some amount in the direction of the gradient. And if you think about that sort of many times over, right, you just end up getting this this expression. Okay, Kevin, do you have something? I see you're unmuted.
Oh, I'm unmuted only by mistake. But yeah, this is great.
Okay, great.
I can jump in all the time if you want.
No. It just sounded like you had something to say, so I wanted to make sure that you. Okay, great. Yeah, apologies. The logistics of doing this are somewhat interesting. Okay, so right. So this just sort of gives you some intuition for what's happening every time you take a step when you're thinking about least squares, right? You're just taking your sort of iteratively going in some direction, and it looks particularly nice in the case of least squares. Okay, so the last thing I'm going to say is that if you actually think about logistic regression, right, what we started all of this talking about, right, we weren't actually talking about least squares, and the reason I sort of walked through that briefly is sort of that we'd already seen the expression for the gradient of the least squares loss function. But if we wanted to talk about it for logistic regression, right, the gradient of f of w is just equal to the sum of the gradients of log of 1 plus the exponential function of negative yi xi transpose w, which, I equals 1 to n, right? So just using the fact that I haven't done anything yet, right? But then this, by using the chain rule, is equal to the sum of 1 over 1 plus x negative y I xi transpose w times exponential function negative y I xi transpose w times y I xi. Okay, so this just tells you, if you were actually going to use gradient descent or like implement your own gradient descent, specifically for logistic regression, this is the gradient of the function you care about, and you'd be taking steps, you'd be subtracting off steps in this particular dimension. Okay, all right. So, so just to recap what we talked about today, we sort of reminded ourselves what it means for logistic regression to define a linear separation between data points that we'll label positive and negative. We talked a bit about convexity, and then also sort of what gradient descent does, which is just, it's an algorithm for finding approximate minimizers of convex functions by taking steps sort of in the direction that you would expect the function to decrease. Okay, and next time we'll talk about a particular way to actually speed gradient descent up, and I think that that's all for today. So I'll stick around and answer questions.